You're looking at tracks created with a new free open source program called BioImageXD. This program for live cell imaging was created by crews at the universities of Jyväskylä and Turku in Finland and the Max Planck Institute in Germany. I'm going to walk you through the final stages of this experiment, whose purpose was to compare migration rates of GFP expressing cells treated with different types of conditioned medium. This is what the original images look like, with low signal to noise and high dome-shaped background fluorescence. But BioImageXD has a batch processing feature that allows us to treat multiple folders with multiple images per folder to segment the cells and output the individual object data files. So these are now examples of segmented objects. Each object is a different color, and we're scrolling through different view fields, and you can see that each view field is very consistently treated and very effectively treated. Now we're scrolling through the different time points of a single image set. So once we're happy with the segmentation, we select a procedure to create motion tracks, locate the segmented object file that we've just created, bring in that data, make any necessary changes to the tracking settings, calculate tracks, and export the tracks result file. So after creating tracks, we can visualize them by bringing in the track files that we just created. Single track file, read that data, select which tracks we want to visualize. Zoom in and have a look. And if you like the tracks that have been created, you can go on to the final step, analyze the motion tracks, click on that procedure, tell BioImageXD once again where those tracks are, read those tracks. For each track now we have the time points and the positions, and we want to tell BioImageXD where to put out the track analysis file and analyze the tracks and export the results. So from this set we've got 181 tracks with at least 3 time points in its track segment. And you can bring that data into Excel, identify the source of where it came from, collect the sites of interest to you, and then bring up a pivot table where those results can be summarized, including, for our example A01, we had 181 tracks. The average of the average speed, the average for 181 tracks, each of which is average speed is included in a grand average, and then that data can be brought out and summarized in a table. And finally, at this point, I want to share with you a conclusion that I've reached after almost 15 years of trying to figure out how to handle statistics from experiments like this. And that is, when we're comparing between treatments, we're necessarily comparing averages between different view fields. And so even though we obtain a standard error for the number of tracks that are included in the average for a given view field, we really need to look at the variance between view fields as a basis for comparing between treatments. And so one approach to estimating the variance between view fields is to acquire replicate view fields within each treatment and take advantage of the fact that the variance of the sum, or in our case the difference of two numbers is the sum of the variances of those individual numbers. And so the variance of the difference between two numbers can be found by acquiring the difference of each set of replicate pairs and finding the variance of that set of differences. And this variance should be twice the variance of the individual numbers that go into each replicate pair. And so if we divide that variance by 2 and take the square root of that, that's an estimate of the precision associated with each individual view field average. And then there's a further advantage to running duplicate view fields in that the standard error associated with the average of this duplicate pair is the standard deviation associated with each member of that pair divided by the square root of n, which in this case is the square root of 2. And so for comparison between treatments, the standard deviation, what is called the grand standard deviation or pooled standard deviation, is estimated as the standard deviation of the differences divided by 2. And so then this pooled variance, in this case 0.45, is a fair approximation of what's being called S x1, x2 here, for calculating t-value and for calculating p-values based on the t-test. So we found BioImageXD to be an incredible program for tracking. It handles everything from start to finish, and this is just one of many strengths that we would like to look into further. So if you are interested in this and would like step-by-step instructions or training, we would be happy to try to help you. And thanks for listening.